Hello and welcome to the chapter 16.2 lecture on double integrals over general regions. So last time we talked about double integrals over rectangular regions, but we're going to take a double integral over a region that is non-rectangular. And the rigorous definition is quite analogous. It would be the sum of the volumes of the rectangular solids as their bases go to 0 in area, no matter how they're sliced. And we call that the double integral over that region R of the function f of xy dA, where that function f of xy would be some surface over the xy plane. And the double integral is the volume depicted here above R. And to find the volume of a function z equals f of xy above a region that is, say, bounded by two curves, we follow the same method of horizontal or vertical slicing that we did for rectangles. And the only difference is that now the integrals that we'll use to evaluate our cross-sectional areas will be non-constant in their bounds. So the picture might look something like this, where we have our function z equals f of xy above the xy plane and want to find the volume of that above some region R. And we'll integrate the cross-sectional area A of x, as x ranges from A to B in this case. And to find that cross-sectional area A of x, well, that would be the integral from g of x up to h of x, if it's this region bounded by these two curves. So for example, let's find the double integral over R of 2x squared y dA, where R is this region. And to be clear, we're not finding this area. We're finding the volume above this area of the function 2x squared y. So the actual picture would look more like this, where here's that region R on the xy plane, and this is z equals 2x squared y above it, and we are finding the volume bound between that surface and the xy plane above this region R. And we'll do that by finding these areas of slices for each value x, and then integrating those dx between this point and that point to add together all of those areas dx, which is adding together a bunch of tiny volumes. So how can we think about this? Well, what is that a of x? Well, that a of x would be the integral from 3x squared up to 16 minus x squared of the height of the function, 2x squared y dy, where that dy indicates that we are moving parallel to the y-axis. Y is going from this point to that point. So this integral here at any fixed point x would be this area depicted right here. And then when we multiply that by dx, then the picture looks something like this. Multiply that area by dx, and we have a little volumetric slice. And then when we integrate those, meaning adding them together for all the x values between here and here, then we'll in total get the volume underneath the surface. And in this case, that would be between x equals -2 up to x equals 2. So our integral ends up looking like this. The inner integral is this area, and then we add together all of those areas times dx between x equals -2 up to x equals 2. And from there, it's a matter of integrating this dy. Okay, well, integrating that dy, then x squared, x is a constant, so integral of y is 1/2 y squared times 2. We have x squared y squared, then we evaluate that between these non-constant bounds. That's the key difference between this and the previous section. But evaluating between two non-constant bounds, that's no problem. We just plug in this as the upper bound and plug in this as the lower bound. And to be clear on what this is saying, since they kind of skip a step here that might make it less clear, we're taking this 16 minus x squared and plugging it in for y at the top. And then we are subtracting the same expression, but now with the lower bound plugged in for y. And then they took this, they factored out the x squared that's common to both, and that's this expression here. And from here, then it's just a matter of integrating that between -2 and 2, but that's just a polynomial. And one can do that and evaluate that it's 663.2 approximately. Okay, so if you were comfortable with the integrals in 16.1, this isn't too big of a conceptual leap. It's just that now your bounds are not constants like a to b. They're possibly bounds of functions, like in this case, 3x squared up to 16 minus x squared. So this theorem really just says the setup for what we have done. I don't recommend memorizing this theorem at all. Instead, just think through it in the way that we did over here, imagining these slices and setting up the double integral. Now, Fubini's theorem said that you can swap the order of integration for constant bounds for integrals over rectangular regions, and what you get is the same thing. However, that very much does not apply with non-constant bounds, integrals over non-rectangular regions. So, for example, if we wanted to integrate sine of x squared over this triangular region, and we were to slice this way, then we would be integrating from x equals y up to x equals pi dx, and then integrating that between 0 and pi dy. However, if we were to swap dx and dy to slice the other way, then we very much would not just be swapping these two integrals. This y can't be on the outside regardless, and slicing the other way, we wind up with different bounds. Slicing this way, we would be going from y equals 0 to y equals x, and then integrating that from x equals 0 to x equals pi. And the best way to swap the order of integration is really just to draw or visualize the picture and just figure it out manually. And another point of this is getting to what we talked about at the end of last time, which is choosing a convenient order of integration. So slicing this way, integrating sine of x squared dx is just actually impossible in terms of elementary functions. However, integrating sine of x squared dy is easy because sine of x squared is constant relative to dy. So that's a direct integral, and then once you do that, you can also integrate dx. So again, if one order of integration creates a very difficult or even impossible integral on the inside, try integrating the other way, and it might become much easier. And we can find the volume between two surfaces, just as you had done when you were finding the area between two curves. So recall from Calculus 2 that given two curves, if you want to find the area bound between them, then all you do is you integrate from the lower bound to the upper bound of the higher curve minus the lower curve dx. Well, it's the exact same thing with surfaces bound between, well, it's the exact same thing with volumes bound between two surfaces. All you do is you take the difference, the upper minus the lower, and you integrate that over the corresponding region. Let's do an example. And one of the purposes of this example will be to find what exactly that bound R is. So let's find the volume of the region bounded between z equals x squared plus y squared and z equals 2 minus x squared minus y squared. Okay, so first visualizing these. This is an upward-facing paraboloid, while this is a downward-facing paraboloid, and this one begins a bit higher. So in total, we'll wind up with the three-dimensional analog of the area between two parabolas. And the point is that this guy will be the higher curve, so we'll want to do this guy minus this guy. And over what region R? Well, let's find where they intersect. What is R? Well, the point where they intersect will be where they have the same height. So we set x squared plus y squared equal to 2 minus x squared minus y squared. And we get x squared plus y squared equals 1. So R is the unit circle. X squared plus y squared is less than or equal to 1. Okay, so where R is the unit disk, x squared plus y squared is less than or equal to 1. What we want is the double integral over R of the higher curve minus the lower curve, dA, also known as this. Okay, so R is the area inside the unit circle, and we can slice, for example, horizontally. We could also slice vertically, but horizontally, we would be going from x equals negative root 1 minus y squared. That point comes from solving for x in x squared plus y squared equals 1, up to x equals positive square root 1 minus y squared, which is the other solution to this. So we have an area slice above this line between these two paraboloids, and then we add all of those together between y equals negative 1 up to y equals 1. So this is what our integral looks like. And okay, but that makes us sad because we have ugly bounds, and that will be annoying to integrate. It looks like some trig substitutions on the second integral. We don't want to do that. In the next section, we'll be learning double integrals in polar coordinates, which will make things like this much, much easier. But for now, the thing that I wanted to illustrate was finding the region R over which to integrate, and some more illustration of setting up the integral. Now, sometimes it's necessary to break your region into two pieces and solve for the integral over each one, and then add those pieces together. So let's say we wanted to integrate over this region. We could break it up into these two pieces, R1 and R2. The reason we're doing that is that our bounding curve changes at that juncture. So in R1, we're going from x squared up to 4x plus 12. That's illustrated here. And then that's moving between -2 and 0. And in this case, it's z equals 1, just to keep it simple. And then in R2, we're moving from x squared up to -x plus 12, illustrated here, dy. And then our x there is moving from 0 up to x equals 3. And then we can integrate both of those individually and add together, and we would find our total volume underneath the curve. And notice that we could have also broken it up into regions this way. But if we broke it up this way, then we would have 3 regions instead of 2, and also uglier bounds. This would be a square root if we solved for y in terms of x. So break it up in such a way as to minimize the number of pieces is a good rule of thumb. Let's do a practice problem setting up an integral two ways, dx dy and also dy dx. Let's do a dy dx first, and I encourage you to do it. Go ahead and pause the video. First, try writing the integral of a generic f of xy dy dx over this region R. So in other words, you want to find what would these bounds be if we were to integrate an f of xy over this R. So find those bounds, dx, dy, dx, and then also after that, find what the bounds would be if we were to integrate it dx, dy. Okay, pause the video, see if you can do that. Okay, so first, doing it dy dx, that means that we're slicing first parallel to the y-axis, and it looks like we are going from y equals x cubed up to y equals 4x, finding that area above that. And then we are adding together all of those areas between x equals 0 and x equals 2. Okay, so that'd be our integral dy dx. Now, what about dx dy? Okay, well, if we're doing it dx dy, then that means that our slices are parallel to the x-axis. So we're going from this point up to this point. Now, here's a key insight. We're doing this as a function of a constant y. So we're asking, what is this x value at this y, and what is this x value at that y? So for this y value, this point here would be x equals y over 4. That's solving for x in this equation. And this point here would be x equals the cube root of y. Again, we need to get those x's in terms of a temporarily constant y. Okay, so we would be integrating from y over 4 up to the cube root of y. And then we're adding together all of those little volumetric slices between y equals 0 and y equals 8. So this really highlights how different the bounds can look if you slice dy dx versus dx dy, and also highlights that if you slice dx dy, then you'll need x as a function of y, where the bounds there, and that's often more difficult just because we typically give bounds with y as a function of x. So this illustrates that typically you'll want dy dx as kind of your first instinct. Okay, let's conclude with this example. We'll just do the setup. The point of this example is to illustrate that often the book and homework problems will not give you a picture. Instead, they'll give you the bounds, and you'll need to draw the picture. So suppose R is the region bounded by x equals 0, y equals 2x plus 1, and y is negative 2x plus 5. Okay, so let's draw these curves. So x equals 0 is the y-axis, y equals 2x plus 1, that's y-intercept 1 and slope 2. It'll look like that. And y is negative 2x plus 5, that's y-intercept 5 and slope minus 2. So what is the region bound by these three curves? Well, it has to be this region here. That is our region R. And it looks like the setup for this double integral. So would we want to slice dx dy or dy dx? Well, if we were to slice dx dy, then we would need to break it up into two regions because we would have this juncture here, and we want to avoid that if we can. Slicing dy dx looks like we'll be slicing that way. And that's much nicer. That means that we're going from 2x plus 1 up to negative 2x plus 5 of our function xy, okay, dy, and then dx, we are moving from 0 up to x equals 1. In this case, we can see it graphically. In other cases, you would just solve for the intersection of these two lines. So that would be the setup for solving this problem, and then you would go ahead and evaluate that. Okay, that concludes the 16.2 lecture. Have a good one.